Every battery you have ever owned was built to fail. That is not an insult, it is physics. And for the first time in the history of this industry, a handful of labs and factories scattered across 3 continents believe they finally found a way to cheat that physics. Somewhere between a lab in California and a gigafactory in southern China, engineers are chasing the same impossible dream, a battery that does not slowly die in your garage, your truck, or your basement power wall. Think about why this actually matters to you. Every electric vehicle on the road today is essentially sitting on a ticking clock. The pack under the floor is worth thousands of dollars, and the moment it starts losing capacity, your range shrinks, your resale value drops, and your once cutting-edge car starts to feel like an expensive paperweight on wheels. Now multiply that same problem across electric trucks hauling freight across entire countries, across massive grid storage facilities trying to keep the lights on when the wind stops blowing, and across every solar farm that needs somewhere to put its energy when the sun goes down. Battery life is not a small footnote in the clean energy story. It is the whole story. So why do batteries die in the first place? To understand the breakthrough, you have to understand the crime scene. Every time you charge and discharge a lithium-ion battery, you are putting that cell through a kind of chemical stress test. Microscopic surface films build up inside the electrodes with every single cycle, and those films slowly eat away at the active lithium the battery needs to hold a charge. Heat makes everything worse. When a battery gets hot, whether from fast charging, direct sunlight, or just a brutal summer in Phoenix, the chemical reactions inside speed up. The electrolyte starts breaking down faster, and the internal damage accumulates at a much quicker pace. Then there is the villain everyone in this industry fears the most: dendrites. Picture tiny metallic threads of lithium slowly growing inside the cell, like frost creeping across a window. If those threads grow long enough, they can pierce the thin separator between the electrodes and cause a short circuit, which in the worst cases means fire. This single problem, dendrite formation, is the main reason why the most exciting next-generation battery designs, the ones using pure lithium metal instead of graphite, have taken so painfully long to reach the market. And on top of all of that, the electrolyte itself, the liquid that lets ions flow back and forth inside the cell, slowly decomposes over time, permanently trapping lithium that the battery can never use again. Put all of that together and you get what every EV owner eventually notices: capacity fade, power fade, rising internal resistance, and a battery that quietly gives less and less every single year. For decades, this was treated as an unavoidable tax on owning anything with a lithium-ion battery inside it. But something shifted, and it did not happen quietly in one lab. It happened almost simultaneously across a dozen companies and research institutions that suddenly all started attacking the exact same weak points at the same time. Here is the golden fact that almost nobody is talking about clearly enough. Every single one of these companies making headlines right now, from QuantumScape to Solid Power to CATL, is making a claim. Not a delivered product sitting in your driveway, a claim. And the gap between a press release and a car in your garage is exactly where this story gets interesting. Let us start with the technology getting the most hype: solid-state batteries. Instead of the flammable liquid electrolyte sitting inside a normal lithium-ion cell, solid-state batteries use a solid material to move ions back and forth. On paper, this is close to a miracle fix. It can dramatically reduce fire risk, and it opens the door to using pure lithium metal anodes instead of graphite, which means packing far more energy into the same physical space. QuantumScape has published cell-level performance numbers that turned heads across the entire industry. But here's the part that rarely makes it into the highlight reel. Independent researchers and industry analysts have raised real questions about how reproducible those results are once you try to scale them up from a lab bench to a full-sized automotive battery pack. Solid Power, working closely with automotive partners, has been shipping sample cells for validation and has production agreements in place, but sample cells for testing are a very different animal from a factory cranking out hundreds of thousands of packs a year. Toyota, meanwhile, has been quietly working on solid-state chemistry for years, and true to form, Japanese automakers are taking the most conservative approach of the bunch, refusing to promise a rollout timeline until they are absolutely certain the technology is bulletproof. Then you have lithium metal anodes on their own, separate from full solid-state designs. These promise significantly higher capacity per unit of weight compared to the graphite or silicon blends used today, but remember the dendrite problem we talked about earlier? Lithium metal is extremely sensitive to that exact failure mode, so progress here depends entirely on finding protective coatings, better electrolytes, or solid barriers that can keep those metallic threads from ever forming in the first place. Silicon-dominant anodes are further along the path to your actual actual driveway. Silicon can theoretically store far more lithium than the graphite used in almost every battery on the road today, but it swells dramatically when it absorbs lithium, and that swelling physically cracks the material apart over repeated cycles. Companies like Samsung, SDI, LG Energy Solution, and Panasonic have spent years developing new binders and nanoscale structural designs that let silicon expand and contract without falling apart. And unlike the more exotic solid-state promises, silicon blend anodes are already rolling into current production lines today, not 5 years from now. New electrolyte formulas are quietly doing some of the most important work in this entire revolution, and they rarely get the spotlight because they are not flashy. Advanced liquid electrolytes, ionic liquids, and protective additive coatings are specifically engineered to slow down that surface film buildup we mentioned earlier and reduce the amount of lithium that gets permanently trapped and lost. This is unglamorous chemistry, but it directly attacks the root cause of everyday capacity fade. Manufacturing itself is getting an overhaul too. Tesla and several of its suppliers have been pushing what is called dry electrode processing, a method that skips the traditional solvent-based coating step used to build battery electrodes. This produces thicker, more durable electrodes, cuts down on manufacturing energy use, and according to early data, may reduce the aging effects that come from the traditional wet coating process. And then there is the technology that flips the entire conversation on its head: sodium-ion batteries. Instead of lithium, these cells use sodium, an element so abundant it is sitting in the ocean beside every coastline on the planet. CAT and BIDE have both pushed sodium-ion chemistry into limited commercial products already, and while the energy density is currently lower than premium lithium-ion cells, the cycle life and thermal safety numbers coming out of testing are genuinely impressive. For stationary grid storage and budget-priced electric vehicles, sodium-ion might end up being one of the most disruptive shifts in this entire story, precisely because it sidesteps the lithium and cobalt supply chain drama entirely. Researchers at SLAC, MIT, and Stanford have also been chasing something that sounds almost like science fiction: self-healing battery materials. Chemistries designed to repair their own microscopic cracks or rebuild damaged surface layers on their own. These experiments are producing real mechanistic breakthroughs in understanding exactly how and why batteries degrade at a molecular level. But make no mistake, this work is still firmly inside the laboratory, years away from anything resembling a factory floor. So who is actually leading this race today? Not in press releases, but in real factories producing real cells. CATL and BYD currently sit at the top when it comes to actual scale and commercialization, combining massive production capacity with steady, iterative chemistry improvements, including their sodium-ion products already reaching customers. Tesla, working alongside Panasonic, continues to push innovation not just in cell chemistry, but in pack design, thermal management, and the software that manages battery health, proving that sometimes the smartest gains come from how you manage a battery, not just what it is made of. Toyota holds a deep and genuinely impressive patent portfolio in solid-state technology, but their famously cautious rollout strategy means they are playing a much longer game than their competitors. QuantumScape and Solid Power remain the boldest bets in the entire industry, the startup swinging for a home run with lithium metal and solid-state designs, backed by real automotive partnerships, but still very much in the scaling and validation phase rather than mass production. Now here comes the question that should be sitting in the back of your mind through all of this. Are we actually witnessing the first real technology capable of making batteries last decades? Or are we still just watching the opening act of a much longer revolution? Because for every headline about a breakthrough, there is a mountain of unglamorous industrial reality standing in the way. Cost is the biggest one. There is currently no solid evidence that any of these next-generation chemistries will be cheaper than what we have today, at least not in the near term. Many of them require more complex materials, more precise manufacturing processes, and tighter quality control, all of which tend to raise costs before they ever come down. Scalability is the second wall. A battery that performs beautifully as a small lab cell tested under perfectly controlled conditions can behave completely differently once you try to build it at the size and volume needed for a real vehicle, produced consistently, month after month, with acceptable yield rates. Safety validation takes real time too, time that cannot be rushed no matter how much venture capital gets poured into a company. Some failure modes in batteries simply do not show up until cells have been through years of real-world cycling across different climates, from freezing Minnesota winters to scorching Arizona summers. And then there is the raw materials question. Even the most advanced next-generation chemistries still largely depend on lithium, nickel, or cobalt, materials tied to complex, often politically sensitive global supply chains. Sodium-ion technology sidesteps much of that problem, but it currently trades away energy density to do it, meaning it solves one problem while creating trade-offs of its own. So where does that leave us right now, in the middle of this decade? Improved lithium-ion variants with better thermal management and silicon blend anodes are already rolling off production lines today. Sodium-ion cells are reaching real customers in specific markets, mostly in stationary storage and budget vehicles. Solid-state and lithium metal cells exist in pilot production, tested and validated in small batches by a handful of automotive partners. Looking ahead 5 years, expect wider deployment of silicon-dominant anodes, a much larger footprint for sodium-ion in grid storage and affordable vehicles, and possibly the first limited commercial solid-state modules if pilot yields continue improving. What almost certainly will not happen within that same 5-year window is a complete industry-wide shift to low-cost, decade-lasting battery packs at full vehicle scale. That kind of transformation needs more time, more factories, and more real-world data than any single breakthrough can deliver on its own. Here is the honest, balanced answer to the question this entire investigation was built around. For the very first time, the industry has multiple real technologies directly attacking the root causes of battery degradation. Not just marketing slogans, but actual chemistry and manufacturing changes addressing dendrites, electrolyte breakdown, and lithium loss at the source. Several of these approaches have already produced genuinely impressive results in testing, results strong enough to earn real automotive partnerships and real investment dollars. Some of these solutions, especially the less flashy ones like silicon anodes, sodium-ion cells, and dry electrode manufacturing, will likely reach mainstream production within the next few years. But the fully realized dream, a mass-produced, affordable battery that confidently lasts decades in your driveway, is still being built, tested, and proven piece by piece, factory by factory. This is not a finished revolution, it is the opening chapter of one. And the companies writing it right now, from a gigafactory in China to a research bench in California, are laying down the foundation for how every electric vehicle, every home battery, and every power grid on the planet will work for the next 50 years. So keep this question in your mind the next time you see a headline claiming the battery problem has finally been solved, because the real answer is far more interesting than a simple yes or no. To make sure you are never caught off guard by what comes next in this industry, join us here at Driven to Distraction.